Yeah, that's really interesting. I think the last thing I want to cover is sort of the future of cosmology and how you see it going. So it seems like, as you mentioned, in the past 5 years or so, maybe there's some new evidence that might be challenging the standard view. Maybe the
Hmm.
standard view is correct. After all, maybe there's some challenges there. What sort of experiments are aiming to collect more and more data that eventually will uh, help us decide between whether the cosmological principle holds or not? Where does cosmology look like to you in perhaps 5 or 10 years from now?
Okay, so let me just lay the landscape first. So I was at a meeting in London last year at the Royal Society on about basically anomalies in cosmology, and it wasn't like a fringe crackpot meeting. There were leading cosmologists there. There was Nobel Prize winners, etc. Um, so people do acknowledge that something does feels a little bit off at the moment. Now, the question is, does it feel a little bit off because we have now gotten to that stage in cosmology where we are collecting huge amounts of data and we're interpreting it in a particular framework? And of course, our framework, of course, was the simplest framework that we had. Is that the problem, or is there something fundamentally broken? And so there are a number of tensions that people talk about. The most famous one at the moment is the Hubble tension, right? So this is the measurement of the Hubble constant as measured by the cosmic microwave background as opposed to the cosmic distance ladder, which is looking out into the universe and trying to measure Hubble's constant from nearby stars to distant stars to galaxies, etc. And they disagree, and they only disagree by a few. One is like 67, the other is 72 kilometers per second per megaparsec. But we've collected so much data now that the error bars on those individual measurements have shrunk and they don't overlap. And that's when you get attention. And so there are arguments there. Is it that there's a systematic in one of these measurements that hasn't been accounted for, which would mean the observations would slide and be in agreement? Or if we keep measuring, are the error bars going to get smaller and smaller? Because if that's the case, there are, again, large numbers of ways that you could fix that anomaly and fix. Number one is you could have dark energy changes with time. So currently in our standard cosmology, we assume that dark energy is this constant, but it could change. It could change its density. It could change its properties. Its tension could change, etc. Again, there's an infinite number of ways that you could do that, or it could be related to the fundamental makeup of the universe. So there's that tension. There's what's known as the sigma 8 tension to do with the rate of clustering in the universe. There's bulk flow tensions that we are seeing large-scale motions, much larger than we can see. There's this cosmic dipole tension, etc. So these tensions are recognized. And I think everyone understands that we are, like, as always in astronomy, we are going to need to get more data, because we always do these kind of measurements essentially at the hairy edge, right, where your data is coming in and you're still trying to understand your data. But we are approaching a point where there is going to be a step change in our understanding in terms of observations. So no, this year, it's 2025, LSST in Chile is going to come online, which is going to basically look at the sky every single night and get the deepest view of the sky. We have the SKA here in Australia and South Africa slated to be online by the end of the decade. That is going to completely change our view of the radio sky. Plus, then there's Euclid already up there taking deep images, and Sphere-X, and all, there's a whole range of new instruments coming online, and they are going, I mean, there's the fire hose analogy, right, for the flow of data. It's going to be huge, right? We will have lots of data. If we had to bet about which path we're going to go down, I think it would depend on who you talk to. There are definitely some that think that the cosmological model, the underlying cosmological model, is fine, and what's missing is the physics of the universe, that the physics of galaxies and stars is more complicated than we've taken them to be, and we haven't fully accounted for that yet. And so you've probably seen this with the James Webb observations of early galaxies. Is that a problem with cosmology or a problem in our understanding of galaxies? And it depends who you talk to. There are others, of course, that lean the other way and are saying that we expect that as we get more data and we expect that these tensions and anomalies become sharper, that we will have to go back to the drawing board, right? At some level with something. It might just simply be the physics of gas or something, or the physics of the evolution of the universe, right? So, you know, I mean, I am definitely, I stand by that statement. I can't remember who made it. You know, prediction is difficult, especially about the future. Right? I would I would lay a sort of even bet at the moment. I couldn't say which way it's going to go until we start to get that data coming in. But of course, it's going to be interesting and exciting, and hopefully, you know, keeps my salary running for a few more years. But but yeah, it's really hard to say, right? Anomalies, when they turn up, can either be interesting or they can vanish. And we only have to look at my colleagues in particle physics who get excited at the smallest bump. More data, it goes away. It might happen in cosmology too.